Hello everyone, I want to use this video to go over our lecture number 3, spatial data models. Let me share the screen. Okay, so this is our lecture number 3, understand spatial data. More specifically, we are going to learn how we use spatial data models to represent our spatial data. Those are the readings. If you have fundamental book, you're going to read chapter number 2 and OER book, chapter number 2. Okay, those 3 sections. This is lecture outline. We are going to address the following 4 questions. Okay, we are going to study what is spatial data and what is spatial data representation. And we're going to learn 2 basic data models, vector data and raster data. Okay, and the last but not least, the team data model. It's very useful, but you will encounter that maybe just when you analyze the terrains of this. So I put it a star over here. Okay, so let's do some review. So in lecture number 2, we learned what is GIS, and GIS can help us on something, right? So GIS can help us understand the world in a geospatial way. So spatial is special. So you can see here, we collect our data, spatial data, geodata, right? And based on the data, we can extract spatial information or geo information. And GIS is right here that can help us to do these things, to store, to represent, put those real world data into this GIS system. We call that data storage, okay? And can manage those data, okay? And can make a map to present it, okay? Can analyze it. So to review the knowledge and wisdom behind the data, behind the information, right? To allow you to see other people cannot see, to analyze the data, to visualize your analysis result as well. Okay, so GIS is right here. So you can see, put the real world data into the system is the number 1 thing. That is called spatial data representation. So when you collect the data with, for example, GPS, you have a bunch of numbers. How you put those numbers in GIS, right? So we're talking about data representation. So another thing you want to keep in mind throughout the semester is the 4 aspects of the geographic information, or GIs. Okay, we have 4 aspects: location and thematic attributes. Those 2 are must-haves. Okay, doesn't matter which project you're working on, as long as it's spatial data, you have those 2 aspects: location and thematic attributes. Okay, so for example, hurricane, for example, your GPS data, you must have longitude and latitude. And for the thematic attributes, you probably save that in a table, right? Like this one, for hurricane, you have wind speed, you have pressure, you have storm type. Okay, and those 2, spatial topology and time, they're optional. Okay, spatial topology is the spatial relationship between one spatial feature like hurricane and another spatial feature like, for example, Caribbean islands, Cuba, right? Or Florida, the state. Okay, so you can see this is the relationship, the track of the hurricane just to the east of Florida, cross Cuba, right? So this is a spatial relationship. When this spatial relationship is important in your data analysis, in your project, you want to encode the relationship in an explicit way. Okay, so we're going to learn how we can do that. And time is still in the study, how we design a better data model to represent time information, time dimension in our data model. We still are doing a lot of research in this field for the new data model, which can more efficiently represent time. Okay, but now the common practice is to use time as one column in your attribute table. So we basically treat time as one of the attributes of each record in your data table, each row in your data table. Okay. Okay, so like I start here, those two, you must have them. What is representation? Okay, so if you look at in a dictionary, representation is a description or portrayal of someone or something in a particular way as being of a certain nature, which is very mouthful, but let me show you this. This is the big rock, right? A representation of this rock is to portray this rock, the shape, right? The shape of this rock is round. So you can see I basically represent this rock with this oval shape, right? Or I can represent that like this. It's more like an artist drawing, right? Okay, so you can see, well, the representation is not just one answer, one standard answer. You have this nature, you have the real world in your, you can have multiple representations of the real world, right? So representation is not the real world, it's a model of the real world. Another example, I can show you this. You probably have this drone image. You see a lot of drone images, right? This is the drone images we captured in 2018 on that VIP day on our main campus. Okay, and this is the representation of our main campus. You can see it's not everything, right? You have palm trees in the drone video, but you don't see palm trees on this map. Map is a representation. Map is not the real world, okay? And here, when you consider, represent the real spatial data in GIS, okay, you need to keep those two things in mind. We cannot represent everything. Like previously, this map, you cannot represent everything. You cannot represent trees because the map scale is too small. We are too zoom out, right? If you represent the trees on this map will be too crowded, too busy, too overwhelming. Okay, so that is the number one thing. So selective, select the things in the real world you're going to put on your map to build your representation. Okay, so you want to answer this question, what to represent. Okay, and you cannot represent all the details. Even you put this thing on the map, let me go back. So you can see all these buildings, you have that on the map, but you cannot represent everything on that map, right? You cannot represent every details. So for example, our roads, for example, our coastal line, you cannot represent every single curve, right? So there's another thing, we call that simplification. On the map, your data, the representation, the model is actually a simplified version of the real world, real spatial feature. Okay, so now you're going to consider your scales. If you too zoom out, you need to simplify a lot. Okay, and also time scale. Time scale, if you cannot represent that many periods, you want to simplify it, right? Okay, so then what to represent to answer that question? You can see selective, right? What to represent? Here are the two types of geospatial phenomena you can represent in GIS system. Okay, so based on spatial continuity. So what's that? Okay. If you want to represent something, you have defined a boundary. For example, our house. Here you see the house. For example, our roads, you see the border of the roads, right? those objects, they have defined boundaries, and you know, oh, here is the house. That is not a house at that location, right? So those we call them discrete objects. Okay. Opposite, you also have those continuous surface. Look at this image. This is Hollywood. Okay, you see mountains. You see behind Hollywood Hill, that is our valley, San Fernando Valley, right? Okay, so then this terrain surface is continuously varying across our geographic space. You cannot just define a boundary. This is of this terrain surface, right? This is, can you draw the boundary of this mountain? It's gradually changed, right? So in that case, we call this type of phenomenon continuous surface or fields, okay? Terrain is very good example. Another thing, temperature, right? Temperature is varying continuously across the space, and also air pollution. They don't recognize boundaries, virus, and soil moisture, right? All these are very good example of continuous surface, okay? So then those two basic types, how to represent those information in our GIS, okay? So let's start with discrete objects. Discrete objects, well, we use shapes. We simplify them as points, lines, and polygons. Okay, so you can see your house at this zoom scale, zoom in scale, it could be points. Okay, if you zoom in a little bit closer, that could be a polygon. Okay, see, depends on your scale. Lines, of course, roads, rivers, right? Okay, trails, those are good example for lines. Okay, and here again, spatial scale matters. Like LA, when you at this level, it should be a polygon, right? But when you zoom it out very far away, maybe outside our Earth, LA become a point, right? Okay. And for the roads, if you zoom in really close, you better represent the roads as polygons, okay? To recognize that width. Then continuous surface. Since we don't have defined boundary, we have this idea, okay? We use grids or raster. So basically imagine yourself have this big fishnet, cover the geographic space. And in each grades, in each square right here, let me annotate. In each square over here, you want to record what's in that square with just one value. Okay, so for example, in this square, you can use, oh, this valley. Okay, but this square, this is Hollywood Hill, right? And this square, so for example, this is, I don't know, maybe residential, right? You see now there's a problem. For those two square, they're good because they're relatively uniform. But for this one, it's like a mixed. You have trees, you have houses, you also have mountains, right? So this actually is one of the drawbacks of this data model. We're going to talk about it later. All right, so to summarize, same real world, you have multiple ways to represent it. Can be raster. Okay, so you can see you have this giant fishnet. You cover the entire surface. You record one value in each grades, in each raster grades. Okay, or you recognize those objects with defined boundaries. For example, you have a river, you have woods, okay, those can be polygons. You also have your house. This will be your vector data model. Other things, those U means unknown, I don't know what's there, okay? Well, you can ignore that in your vector data model, okay? All right, so then GIS, you have those two data models. You need to put those at least location and semantic attributes into your data model, right? You cannot just draw a bunch of geometric shapes or a bunch of square, just that, right? We also need to put those information into our model, okay? All right, so then let's start with vector data model. How to record the location? Very simple. For points, you just need to record X and Y in your data model, okay? And for lines, you need to follow a sequence. See, I start from X1, Y1, I end with X6, Y6, okay? And for polygon, you also need to follow some sequence. So for example, from X7, Y7, go to X8, but you're going to come back to X7, Y7, right? Okay, to enclose this polygon. So in GIS, QGIS or ArcPro, those GIS software, they will know this is the polygon, it's not the line. Okay. All right. So as you can see here, just keep in mind, this one I just record location. I didn't record the relationship. For example, this wood was number 1 is to the east of this river. In my data model, in this case, I have no place to represent this relationship, right? So we call that this type of vector data model entity by entity data model. So basically, we just record them one by one. Okay. We also call them spaghetti data model, as you can read in your textbook. No topology whatsoever. Okay. All right, then semantic attributes. Semantic attributes in vector data model is stored in table. Okay, but you can see here for each row, that is, we call that a record. In this case, that can be one state. Okay, and for each column, we call that a field that represents one of the attributes of your record, of your spatial object. Okay, so you can see here, in this case, that is state name is one of the attributes of each state, right? And ID is each state. Okay, so one column is called field, and the one row is called one record. Okay, and in GIS, when you add fields, okay, you're going to click on this button, you choose add field. But here you can see you have additional questions. Okay, this is called type or data type. Okay, you need to specify what kind of information is stored in this column. So for example, for this color, that should be a text, right? And for this sheet number, that should be a number, right? So you can see you have two general types, qualitative or quantitative. Okay, for qualitative, that can be text. Okay, special text can be date. Okay, but for quantitative, you have short integer, you have long integer, you have float, you have double. What's that? Okay, let's explore that. Okay, here, quantitative and qualitative. Okay, and here, those quantitative and qualitative information, actually you can break that down by their type of measurements, okay? Type of level of measurement, okay? So we call them nominal, ordinal, interval, and ratio. So what are the nominal data? Those are the names. Okay, so for example, the name of the state, the name of the state. Okay, so like this one, okay? Second one is, here we go. Ordinal is the ranks. So for example, the largest state to the smallest state, right? It's still a qualitative information, but you do have this comparison going on in this column. Okay, so we call that ordinal data. But those two types, we all put them in as a text, okay, as a qualitative information. Okay, quantitative information, you have interval, you have ratio, but you do have integers and the data have the floating points, right? You have the digits, decimal digits. Okay, so that is you put them into float or double. Can be either way. Can be either way. It's just the double is more accurate in the storage, but takes more space. Okay, but float, you also have the digits, takes smaller space but less accurate. I would say that way. Okay, all right. So that is for those quantity information. So you may ask, what's the difference between interval and ratio? Well, interval is difference is meaningful but not ratio. For example, you can say population is a ratio because you can say this country has twice large as population at the other country, right? But temperature, for example, is an interval. Temperature, the difference between one number and another number is meaningful, like 10 degree high, 5 degree below, right? But like 20 degree, it doesn't mean it's twice warmer as 10 degree, right? It's make no sense. Okay, so that is interval is meaningful, but ratio is not meaningful. Okay, and here for interval, you don't have absolute zero, okay? But ratio, you have absolute zero, okay? All right, so then the types in the computer system, you have all these choices, okay? Like I said, don't be overwhelmed. Just a big text for your qualitative information, okay? If you have integers, you can put short integer or long integer, okay, as integer, and float or double as you have decimal points. Okay, the difference is you have different space to store those numbers, and long integer compared to short integer is more accurate. Okay, you have more digits, and the float versus double is more accurate. Okay. All right. So more importantly, when you put your data in the table, okay, a very important thing is you want to perform this analysis called table join. Okay, because through table join, you can bring different tables together. Okay, you don't have to maintain this giant table to have everything just in one table. You can separate them into smaller tables. Then in that case, it's easier for you to manage your data, to update your data, to keep your data integrity. Okay, so well, why? Because before we learn how to do our table join, here are a few terms you want to memorize, you want to know, okay? So here, each table, you have this primary key. That is a unique identifier for each row, okay? And you know this, you know field, you know record, okay? And here, for example, here, you have two tables. You have this tree wood table, okay? You also have this land ownership table, okay? How to bring those two tables together? We are going to rely on those common field. So what is common field? Common field is not necessarily to be IDs, okay? It can be just a normal field, normal attribute column, but those information shared across tables. Okay, so you can see here in this table, I have land use code, including the same information as a land use code here in another table. You can also use a different name, but the information here, the data here, you need to stay same. Okay, land use code 300 in this table means the same thing as land use code 300 in this table. Okay, so in this case, you can match them. We call that table join. Okay, so if this is 300, I will attach national park at the end of this table. This is also national park, right? And 350 is private. See here, that is the end, the result of your table join. See here, okay, national park, and private. because I have those codes. Okay, so you can see here, if you change ownership, 300 is not national park anymore, it become private, then in this case, you just need to redo table join, and you can update your original table, which is important, okay, which is very efficient, I would say, okay, save you a lot of time. Imagine you have like a thousand of records. You don't want to do that manually, right? Okay, so then here's another important thing. You can see this is my join table. The structure is based on this table. So we call this table is the target table, okay? All right, so then another thing, another example I can give you is apartment and the key, right? And this apartment building, see, you have different field name, but same information. So then you join this information to your table 2. Your table 2 is your target, okay? So you can see here for each building, I have this key, then I know I hope I know the building type. Okay, so this is a spatial join. This is called one-to-many. Okay, one column, one key information can be attached to multiple records to your targets. Okay. Okay. So then with that, the next thing you want to know is the common data format of vector data model. Shapefile is a very commonly used data model you can find out there online. Okay, so it's non-topological. Okay, but when you download it, you unzip it in some cases, and you can see one shapefile, you have the same field name, but different file extensions. They all belong to one shapefile, which is this census UTM Z10 North. Okay, the same shapefile, but different format. Okay, so that is why I don't recommend you manage your shapefile just in a plain folder. Always do this with our GIS software. Okay, Acro or QGIS in a data manager, in a catalog, or your QGIS data manager, you will just see one file, not just multiple files. Okay, so this is one thing. Okay. Topological information, again, is a relationship between different spatial features. And you can see here, you can define many relationships between line, polygon, and points. Okay, so then why topology? Because that can enable network analysis. Okay, so in our GIS 23, we are going to learn how to perform network analysis. Then in that case, you're going to encode this topological relationship in your data. Okay, and there's a lot of many benefits to have this topological information encode into your data model. So for example, you can enable this topological editing. Okay, in this case, you know, the yellow polygon and purple polygon here, they know they're next to each other. Okay, so when you add this boundary won't have any gap. We could add silver polygons. Okay, I'm sorry, sliver polygons like here. Okay, you don't have any because they know they have to stick with each other. Okay, but in this case, non-topological editing, you don't know they're next to each other, right? They share the boundary, so you will end up with a smaller polygon. We call that sliver polygon, S-I-L-V-E-R, a sliver polygon here. It's also very efficient in the data storage. So in our live meeting, let's watch this video together. Okay. All right, then how to encode your topological information? Just the knowledge part, okay? You need to define some, give them different name, unique name for those points and line polygons because they have different, they play different role in your topological data model. So for example, for your start point, and endpoint, we call them node. Okay, and if that point is used to define the shape of the your lines, okay, we call them shape point or vertex. Okay, or vertex. Okay, if you just have one line, okay, and this is the end node, right? This one line is not intersect with or joined to another line, we call that downlink arc. Okay, so you can see all these terms we need to use to define our topological data model. Okay, and arc basically is a line. It's a line. Okay, and face is called polygon or face. Okay. All right, then how to encode it? Okay, first, this is the Esri spatial coverage in this specific data format. They encode their topological information in this way. Okay, this is the simplest version. So let's just go through it and you will have a sense how this topological information can be encoded. Okay, so first I need this point attribute table. Okay, I will record each point. I will have the coordinates of each point. Okay, so this is number one. Number two is I'm going to use those coordinates to also encode my arc. Okay, so you can see arc number one will be 1, 11, 1, and 10, right? And then arc number two will be 6, 10, 9, 7. Okay, or maybe starting from here. Okay, so you can see I will encode the coordinates to build this arc coordinates first. And then I need to build this relationship, end node and start node and end node, right? So arc one start from where to where. So in this case, your arc will have some direction, right? We call that directional arc, directional arc. So for one, number two, start from 2, 2, end with 2, 3. So right here, this is the end node. Okay, and all these red dots in between, that is your shape points or vertices, right? Okay, so in this case, we don't have to because we have them here. Okay, so this table specifically define the relationship between arcs and nodes. Start from where to which node, right? Okay, then arc and polygon, they have this relationship. So if you follow one arc, on your left side, you have one polygon. On your right side, you have another polygon, right? So this is arc and your left polygon and your right polygon. Okay, and each polygon, you also have this relationship. My polygon is made of which arc or which arcs, right? So you can see here, this arc for 151, this polygon, you have one, arc 1, arc 4, arc 5, arc 7, arc 5 is the entire thing. Okay, then in this case, we put 0 as a special identifier. Okay, means starting from here, after 0, I'm going to encode any arc inside this polygon. So you can see 7 is inside. It's like a donut, right? Okay, so this is how you encode your spatial topology relationship. Okay, you don't have to do this. ArcGIS or QGIS can help you to do this, but those tables, that's how it works at the back end. Okay, what are the data formats? You have topological information, coverage, okay, and Census Bureau Tiger data, okay, and digital line graph in USGS. All these data, they are topological vector data models. Okay. All right, so here let's summarize the pros and cons of vector data model. Okay, they encode individual objects, means you can pinpoint that objects, means the location and shape, they are very, very accurate, okay, as long as you have enough points to, depict, to portray the shape of your lines and polygons, okay? And we use a table. We use relational tables. You can join the table, right? We can use tables to store the information, the attributes, which is very efficient and very easy to manage. Okay, and spatial topology, if you need, you can encode it, but compared to raster, raster cannot do that. Okay, and it's compact. Usually your vector data file have very smaller file size. Okay, but the data structure compared to raster is a little bit complicated. Okay, and it's a little bit complex for spatial analysis at the back end. Okay, but you don't feel that. Okay, you don't feel that. Okay, so then the design of the raster data model. In this case, we also need to use encode our location and thematic attributes, right? But spatial topology, we cannot do that. Okay, so let's start from location. In raster data model, you don't have to locate each pixel. Okay, you just need to record two pieces of information. One is the starting point. It can be top left, can be lower right, can be any of the four corners. Okay, and then you're going to define cell size. That's it. So you may ask, Jing, then how can we locate this tree? Okay, you just need to calculate. So for example, from the starting point, how many pixels to the east, how many pixels to the south. Then you add the pixel size to this location coordinates, you will get the coordinates of here, right? So you don't need to represent location of each grids because in the data model, it's just a matrix of pixels or cells or grids, okay? All right, and speaking of attribute information, well, one pixel or one value, one element in that matrix can only store one information, right? So each pixel or each cell contain one value and only one value. If you want to store more, for example, here, I record land coverage, land use types. If you want to record temperature, you're going to create another matrix, another layer, okay? So that is how you record attributes. No topological information can be represented. So pixels, they don't know who next to itself, okay? Okay, so here you can see this is attribute table you will see in your GIS software. Unfortunately, you cannot see those matrix directly. If you want, you can convert it to a like plain text file. You can do that, but here in the attribute table of in the GIS software, they basically just summarize how many pixels contain that value. Okay, so this is the summarize of all the pixels who have this value number 1, for example. Okay, so this is attribute table. And spatial analysis, especially spatial overlay with pixel, is with raster data model, is really simple and easy, straightforward. Basically, you just match the pixels with same location, and you can do a lot of calculation across different layers, different raster layers. So for example, here I have soil layer, soil attributes at this pixel, and the same pixel, but in a different layer, forest, right? And a different layer, coincidence, okay? So here you can combine all these values together to do your analysis. We call that spatial overlay, okay? And well, raster data model also have drawbacks, as you can see here, because pixel size is important, right? If you want to really represent your spatial features like farm, the shape in a very accurate way, you need to use a very small pixel size. But the downside is your raster data set will have a very large file size, right? So, but if you reduce the pixel size, you can see the form, the original shape will be lost. Okay, so you constantly have this trade-off between pixel size, spatial details, okay, and your storage space. Okay, and another issue related to raster data model is this mixed pixel. We talked about it when we look at the Hollywood that image, right? So for this specific pixel, what should you encode in this pixel, right? This mixed, you have grass, you have trees, you also have houses. Okay, so this is the issue. Well, common practice is we put the majority, but what if there's more? It's no majority, it's just mixed. Maybe you put mixed in it. Okay, so that's up to you. You are the designers. You are the designers of raster data model. Okay, so when you do the analysis, raster data also have this issue. Pixel size doesn't match. So in that case, you need to do one thing called resampling. You want to unify the pixel size, the pixel sizes across different raster data layers so that you can match them. You can do your spatial overlay in this case. Okay, so you can see all these raster data layers, they should have the same pixel size. Okay. Okay, so pros and cons. It's simple. Spatial overlay is easy, and well, it's large. The shape cannot be precisely represented, and location is not precise. Okay, and topology, there's no topology. The pros here, well, why I say it's easy, because you can always just change the pixel size to make your shape more accurate. Okay, so this is what I mean. Okay, mixed pixels is another issue. Don't worry, you can convert them from vector to raster or raster to vector. But I would say do that as minimum times as possible. Try to avoid it as much as possible, because every time you convert, you lose the shape, you lose the accuracy. Okay, so this is conversion, especially from vector to raster and back. You can see you will lose a lot of information regarding to shapes. Okay, and the team model represent a triangulated irregular network. So you can see one of the downside of raster data model is the file size could be very large. Why? Because we use a fixed size of that pixel, right? So what if you have this, let me show you this. You have this area, very flat. You record the elevation in those pixels. All these pixels have same information, right? That actually is a waste of space. You only need to have very fine or smaller pixel size for those mountainous area, but not for those flat surface. But in raster data model, because you have to use a unique size, well, then the file size is very large, but not team model. Team model, like you see in the definition, is an irregular network. We basically use triangles, like you see here. So you can see I can use larger triangles or polygons to represent those flat area. I can use smaller triangles to represent the mountainous area. Then it's more flexible, right? So I can still maintain the very accurate shape of this mountain, but reduce the waste of space across this flat area. Okay, so this will be the main advantage of your team model. Okay, then how to create your team model? Well, first you need to sample points on your surface. That can be elevation, that can be temperature, okay? And when you have those points, you are going to build those triangulations. Note, there's not just one way to build those triangulations. Means your team model and my team model may be different. Even we are building the model for the same location, same area. Okay, so this is how you build your team model. Okay, so here back end, well, you can see those are my points. I run some triangulation algorithm. I can build those triangles. Okay, and then my attribute table. I have this node attribute table. So my points, where they are, what's the height or what's the temperature of each node. Okay, and I can partially actually record the relationship. So you can see I have many triangles. Okay, I can have define my nodes. Okay, I can define my neighbor triangles. Okay, for this A, I have neighbor. I don't have any neighbor here, but I do have J, I do have B. Okay, it's good to follow certain order, like clockwise or counterclockwise. Okay, but you don't have to just always follow one way. Okay, just make sure in one table you follow the same way. Okay, so pros and cons is compact. Okay, can be very useful in your terrain analysis. Okay, and it's easy to represent the structure of the surface. As you can see here, I can easily make a 3D view of our terrain. Okay, and here the downside is, well, it's very hard to build and it's not unique. Okay, it's very difficult for spatial overlay because you don't have the same like polygons, same pixels, right? Or the same way to define your polygons. Okay. All right, so let's compare it. For continuous field, you want to use team model or raster data model. For discrete entities, just go with vector data model. Okay, and here, in most cases, you will just use vector and raster. But if you are doing some terrain analysis, like you analyze how steep that slope is, you want to visualize the 3D terrain, consider team model. It's more efficient. Okay, so here's the summary of the pros and cons of those data models. Okay, we talk about it in our lecture presentation already. Okay, just a summary table. Okay, so I think this is the last slide. In this, let me go back to summarize what we learned. Okay. We learned what is spatial data representation. Make sure you know data representation is not the real world. That might be right. I have many ways to represent it. Okay, so then when you build a data model, you want to select the things you want to represent. You want to simplify because you have to, your map have a scale. Okay, and then we learned two basic ways to two types of geospatial phenomena with boundary, with definite that defined boundary, without defined boundary. You see that as discrete objects or continuous fields. Okay, and if you see that in a discrete objects, use vector data model, continuous fields, use raster data model. Okay, and for each model, we learned how to represent location and attributes. Okay, if you need, you can also encode spatial topology and time. Okay, very important vector data model. Your location is like this, just X and Y, or a sequence of X and Y. Okay, for your attribute information, we put it in the table because we want to do table join, right? Table join is very useful practice in when you do your spatial data analysis. Okay, so raster is this fishnet. Okay, one pixel can only have one value. okay? And when you have multiple layers, as long as they have the same pixel size, you can do the spatial overlay very easily. And team model, we use that a lot to represent the terrain surface, okay? But it's relatively hard to build, okay? And make sure you know the advantages and disadvantages of each model, and based on your projects, your purpose, you're going to choose the best fit, okay? All right, so I think that's my presentation, and I'm looking forward to talking to you in our live class meeting so that we can explore more with real examples. Bye for now.